All right, let's get started. Good morning. Welcome back. Any questions before we start? I might go a little fast today because I realize we are a little behind on our plan. But we do want to take a good enough time to understand the basic SVM optimization setup. And then there will be some extensions to that we can quickly go through. All right. So if there are no questions, let's just jump into our discussion, right? We're talking about optimization formulation. It's there up on the board, the first panel, right? We are trying to minimize W, the magnitude of W or the square of the L2 norm of W, subject to certain constraints, okay? And what we do first is that we first write it using the Lagrangian multiplier method in a slightly different form, right? So we say that let's try to minimize, and now since we are going to introduce Lagrangians, multipliers, there will be more arguments here. So there's W that we want to find the B, and then we also want to find all these alphas. So alpha is a vector of n. So if you have n training examples, you have n Lagrangian multipliers, and we define this objective function, which is now a function of all of these three things, right? And it is equal to by 2 plus, we bring in all of our inequality constraints up here, right? So essentially what I did was that if you remember on the slide, the inequality constraint in the original formulation was written as this line, right? But when we did our discussions on how to do Lagrangian multipliers, we said that we are going to treat our inequality constraints as g of anything less than equal to 0, right? So all I did was I brought this around, and then our constraint became that 1 minus yn of this thing should be less than equal to 0, right? There's just a little bit of rearranging, but nothing different. All right, now how do we solve this, right? So last time we saw that since this is and then of course subject to that all alphas should be positive, because these are inequality constraints, right? So the first thing we do is we convert it into our max-min setup. Oh, sorry, min-max setup, right? And we showed last time that min-max setup is still going to work. So what is min-max setup? We say try to maximize over all alpha this L of W, this, and then try to minimize over all W comma B, right? So if you go back to our discussion last class, essentially what we said was that if we can solve this problem, first this and then this, that will be same as solving this constrained optimization problem, right? So that's something that we did last time. And this is what we call the primal. We can call either of these primal. So this is the primal formulation of SVM. And then we looked at another similar formulation in which we just flip the order in which we do the optimization, and which is we first do the minimization over WB, and then we do the maximization over all alpha. Right? This is what we call dual. In general, the solution that you would, so both of them will give you some W and B, right? There's no problem with that. But the solution that you get from the dual will not be same as primal in general, right? And then we also looked at the situation that the minimum, the value that you'll get from this objective function will always be less than equal to the P star, right? However, if your objective function, which is this, is convex, which is convex in this case, and if all of your constraints are affine means linear, which means you can express them as a linear function of your W's and B's and everything else, then these things are same. Okay, and there's a mathematical proof to prove that, but here we are going to treat that as a given fact that for SVM D star equal to P star. So which means what we will do here is we are going to solve the problem like this, okay? And then because of this strong duality, it will be the right answer, right? Any questions so far? So now the question is, how do we solve this, right? So first we say that we are going to first solve, so the first thing we're going to do is we are going to solve this internal part. We are going to minimize W comma B with respect to LWB thing. So I'm going to write it out. Right? So this is the, this is of course n equal to 1 through n. So let's first try. So let's assume that alphas are given, they are constants, and we are going to minimize W and B with, or we are going to find the W and B that minimizes this thing, right? So what we will first do is we'll say, what is d by d of this? I'm going to call it L, right? Of WB alpha, right? With respect to W, right? And then we're going to set it to 0. So this is going to be, so if I compute the partial derivative, this part's partial derivative will actually be just W, right? Because this is, you can think of, this is just W transpose W, right? It's just the square of all the sums, and d by d of W transpose W is actually 2W. It's just like a square. D by d x of x squared is 2x, the same like that, and then 2 gets cancelled with this. So this part is just W plus, then the partial derivative will move inside the summation. Of course, alpha n is constant, right? 1 will go away, so it is going to be actually minus alpha n, right? Yn xn, because when you compute the partial derivative of this will just be the scalar, right? So d by dw of this is just 1, so it will be alpha and yn xn, right? Imply, and then b is a constant with respect to w, that goes away. And when we set it to 0, setting gives us all right, so this is basically, we minimized this, and now we got w in terms of alphas and x and y. Of course, we don't know alpha yet, right? But we do know yn and xn. So we have made some progress. And then we can also do d by db of lw beta wb alpha, and that is going to be, because this term does not have b, the only thing that is here is this one, right? So it's going to be minus summation n equal to 1 through n alpha n yn, right? Because the b part is just going to disappear when you compute the partial derivative. When you set this to 0, this gives us when you set it to 0, basically this gives us a condition. It does not give us b, unfortunately. So these are the two things that we get. All right, we still don't have an expression for b, but later we'll see we can compute it in some way. All right, any questions so far? All right, now what we do is, since we have both w, we have these things in terms of alphas, we are going to plug them in back into our formulation over here, and then we'll get a objective function which is just a function of alphas, right? Because all your wb's will disappear, and you'll see that. So what we do is we say, substituting w in L, right? So what we'll do is we'll say, now what we need to do is we need to maximize. So let's first substitute it over here. We're going to substitute here. So right, and I'm going to let's do it one by one. So let's just open this up so that it's easier. So this is essentially w dtw by 2, right? Plus summation n equal to 1n. I'm going to move these in. So alpha n, right, minus yn, right, w transpose xn, minus alpha n. So I'm just multiplying everything inside, and minus alpha n y n b. All right, so this is just I just opened it up, right? Then what we're going to do is we are going to use these two results. So we know that w is this, and we know that this summation is 0, right? So we are going to and use summation n equal to 1n alpha n yn equal to 0, right? So we have these two things that we found out by minimizing the previous Lagrangian. Okay. So this can be written as, so what is Wt? Wt is just summation n equal to 1 through n alpha n yn xn transpose summation n equal to 1n alpha n yn xn, right? So this is w transpose w plus summation n equal to 1 through n alpha n. This will stay, it does not have x, w or b, minus, in this one the same thing, yn. Instead of w transpose I'm going to put n equal to 1 through n. Actually, since there's already n here, I'm going to use subscript m. It's going to go from 1 to n, and this will be what is w? Alpha m y m x m, right? Transpose xn, right? So this is, I just substituted this with the other thing, and then this part, now since b is constant, right, so b can be put outside, and we know that this whole part is 0, right? That's what this gives us, which means that there's nothing. This will disappear. Poof, it goes away, right? So which means that this new objective function, which is just a function of alphas, does not have b in it and does not have w in it because we just substituted it. All right, so this is our new, this is called our dual Lagrangian, which we need to maximize now. All right, any questions so far? So now we're going to rewrite it a little bit more elegantly. So what I'm going to do is first write out what how people write it as. So this is going to be a function. So now what we want to do is maximize this L alpha for all alpha, right? And then the idea is that then you get the alphas, right? And then you use those alphas to get the w, because you know what w is as a function of alphas, right? So we solve this equation, which is just this optimization problem, which is just a function of alphas. You will get some alphas, then you plug them back into w, and then you will, I'll show you how to also get b. All right, any questions so far? So this is important. Now one thing I'm going to do is I'm going to rewrite it like this. So L of alpha is actually, so if you multiply these all, right, oh actually I should write. So this can actually be written as two summations. This would be m equal to 1 through n and n equal to 1 through n. Alpha n alpha m y n y m. So I'm just multiplying these two. So think about these two, right? This is a vector and a summation inside a vector, and this is also a vector with summation. When you multiply them together, this is how it will look like. Okay, this part plus this stays, of course, right, minus, but there was a half here too, right, half, minus, and then this thing also, if you open it up, it will look the same. It will be n equal to 1 through n, m equal to 1 through n, alpha n alpha m y n y m x m transpose xn. Okay, so this is the part that, I mean, you can go back and sort of verify that this is true, but think about it this way. Let's say you had a simple situation where you had only one data point, right? In which case this would have been alpha 1 y1 x1, this part, right? There's no summation, there's only one data point. And then you have to do a transpose of this with alpha 1 y1 x2, right? So this clearly becomes alpha 1 y1 y1 x1 transpose x2 x1, right? So this is easy, right? And then you can generalize it a little bit if you're feeling braver. Let's say there are two data points. So now it will be alpha 1 y1 x1 plus alpha 2 y2 x2 transpose, right? Make it a little bigger, right? Times the whole thing again, alpha 1 y1 x1 plus alpha 2 y2 x2, right? And if you multiply them, because the transpose goes in, right? So this will be equal to, these are scalars. Alpha 1 is a scalar, y1 is a scalar. That will be x1 transpose plus alpha 2 y2 x2 transpose times alpha 1 y1 x1 plus alpha 2 y2 x2, right? And then if you just multiply them, they'll look like, okay, alpha 1 y1 x1 transpose x1 plus alpha 1 y1 alpha 2 y2 x2 x1 transpose x2 and so on, right? Which can be written as just a summation alpha I or alpha m alpha n y m y n x m transpose xn. M goes from 1 to 2 and n goes from 1 to 2. Right, so this is just sort of to show how it works out, but you can expand it for a general case. So anyway, so this is what you get, right? Let's go back to this size. And this, since this is just the same thing with half, so this will look like this. Alpha n equal to 1 through n minus, right, half of m n alpha n alpha m y n y m x m transpose x n. So this is our new optimization problem. And we want to maximize this. We want to find max with respect to alpha. Any questions? All right. So here's so let's look at it closely, right? It's a function of n variables, alpha 1 through alpha n. And then there is some constraints here, right? Subject to alpha, all alpha n should be greater than equal to 0. That's the Lagrangian constraint. And then there's also this constraint that this thing, whatever you get, it should satisfy this, because this is what you get from the first minimization. And summation alpha n y n should be equal to 0, right? So this is another constraint for optimization problem. And it is a quadratic constraint optimization problem because your unknown variables are getting multiplied with each other, right? All of these things are known. This is your training data, this is your training data. Only these are unknowns, right? But they're getting multiplied with each other, which means that if you try to solve it using the first principles, like taking the derivative and everything, it becomes a little messy because, you know, whenever you have a function fx and it contains xy, right? Then it becomes a little, because when you take the derivative, you have to do the chain rule and so on. So at this point, what we are going to do is we are going to offload this work, the job of optimizing this, to a quadratic optimization program, okay? So use your favorite QP solver. QP is quadratic programming solver. Okay, any solver that you can buy. I mean, on MATLAB, we have one called QuadProg, and I think there are others as well in C, C++. You can use that to solve this, right? And that's what typically in support vector machine learning, they do that. They use something to solve for this one. Sometimes they also do some more, you know, in-house optimizers as well. But the point that I'm trying to make here is that at this point, I'm not going to go further into the math. We are going to assume that there's a solution, there's some black box that will give us this solution, all right? So let's say, let alpha 1 star, alpha 2 star right? Be the solution of the QP problem. We call it the quadratic programming problem. If you have done linear programming and quadratic programming, I know you know that. The idea is that it's an optimization problem with some linear constraints, and there are solvers that can be used to get that. So let's say these are our solution, right? Which means that once we have these, we can now compute our W. W will just be summation n equal to 1 through n, alpha 1 star. All right, so we can get our W, which we wanted. That's our SVM training. B is a little tricky. We still don't know, because somehow when we tried to do our minimization of our original problem, B disappeared, right? Because B was only getting multiplied. But there is a way to get B. Any questions so far? All right. So one thing you'll remember to get B, right, is that I talked about these KKT conditions, right? The Karush-Kuhn-Tucker conditions, which are these conditions that need to be satisfied if whatever you get is the right answer, right? And those conditions are actually derived from the formulation. There is no magic there, right? So there are the 5 conditions here for this dual optimization problem. The first thing it says is that, of course, the partial derivative of your primal with respect to W should be 0, right? Which is correct. That's how we got our W. Primal partial derivative with respect to B should be 0. That's how we got this. All of the constraints should be satisfied, right? Which is good. All your alpha should be positive, right? And here is one more, which is that the product of your alphas or alpha n stars and the constraint should be 0, okay? Why is this true is a little more involved, so I'm not going to go into that. So let's just assume that this is a condition that is true, all right? And this is mathematically proven, all right? So let's focus on this condition number 3. What this condition says is that whatever solution that you get, all your constraints should be satisfied, right? Oh, sorry, let's go back. Let's look at this one. So what this says is that for every alpha n times that corresponding constraint should be 0. This is a key constraint, right? And that helps us, because if alpha n is greater than 0, right? So 2 things can happen. So let's go back here. So KKT number 5 tells us, KKT constraint number 5, actually what that really tells is that the summation over n equal to 1 through n, alpha n times yn, this is the constraint, right? The inequality constraint, which puts it away from the margin. This should be satisfied, right? And now remember that n alpha n's are all positive, right? Which means that if you have a solution, then this thing will always be positive, right? So if I write it out, so this will be alpha 1 y1 w transpose x1 plus b minus 1 plus alpha 2 y2 and so on, right? The whole of this should sum up to 0, right? Now let's look at each one of these. So this can either be 0 or positive, right? This thing will always be either 0 or positive again, right? Because this is the constraint. We want this to be true. So whatever solution that you get, this will be true. Because what this constraint tells us is that the training data point number x1 should be either on this side of the margin or this side of the margin, depending on what y1 is, right? So this is essentially encapsulating our margin constraints, that your point should be either here or here. They cannot be between, right? Which means that for all n, alpha n will be greater than or equal to 0, and for all n, y1 times w transpose x1 plus b minus 1 will be greater than or equal to 0. So either they will be on the margin, in which case it will be equal to 0, or they will be on the away from the margin, it will be greater than 0. Which means that for this whole summation to be 0, each one of these individual entries should be 0, right? Because they're all positive. So you cannot sum up positive quantities and get 0, right? So the only way this would happen is implies that alpha n yn must be equal to 0, right? So which means that there will be some alphas that you will get from your QP solver which might be 0, and there will be some alphas that might not be 0, right? So if alpha n is equal to 0, then it means that then yn times w transpose xn plus b minus 1 can be greater than equal to 0. So then it's okay, right? It can either be 0 or greater than 0. It doesn't matter because it gets multiplied by 0. So that's fine. But if alpha n is greater than 0, right, then this should be 0. So here comes a very interesting aspect, which means what this says is that, so let's sort of develop this further, which means implies that xn is on the margin, right? Because if this is equal to 0, it means that this point is on that margin, right? Which means that you run your QP solver and you'll get some alpha and alphas. Some of the alphas will be 0, some of the alphas will not be 0, right? So the alphas that will be 0, alpha n that will be 0, the corresponding data points will be away from the margin, whereas the alphas that are non-zero, the corresponding data points will be on the margin, right? So this is actually a very beautiful result for SVMs, because what this helps us do is that when we compute a W, right? Actually, I forgot to put stars here because this is what we get out of this. This is how we compute our W, right? Now, the ones that in which alpha n is 0, right, those are useless for us, right? Because they will not take part in that summation. Right? Those training data points are useless in finding W because for them alpha n star is 0, right? The only ones that are useful for us to compute W are so this is actually same as n such that alpha n is greater than 0. Right? Because the ones that equal to 0 is not useful. And these are all those points that are on the margin, which means that when you compute your W from your alphas, you can discard most of your training data, which is not on the margin. You only use those points that are exactly on the margin, all right, to compute your W. Somebody could argue, why are we doing this, right? But this will become more useful when we talk about kernel SVMs. But here, the point I want to make is that, let's say you ran your QP solver, right? And let's say you had 1,000,000 data points. So now what you would do is, you would get 1,000,000 alphas back. Now, because of this result, what you can quickly do is, you can quickly eliminate all of your alphas that are 0, because they will not help you in finding W anyway. And you can also throw away all of your training data which are not on the margin, all right? So the point is that only training examples that lie on the margin, which means that either they are on the positive margin or negative margin, right, are relevant. And these are called support vectors, okay? And that's why the name support vector machine. Basically, SVMs are defined, you do not need all of your training data. Well, you need your training data to do your optimization. It's not that, because you don't know your W initially, right? So you cannot discard anything. But once you have done the first phase, after that you can discard all of your training data because they will not matter when you compute your W. Any questions? So these are the points that we use for later. So support vector, and that is one beauty of support vector machines, is that it makes our solution very small. So instead of having million alphas, suddenly you will be left with only a few alphas, and typically only a few points lie on the margin. There will be very few support vectors, so which means that your solution will be smaller. Okay, so that's a good quality of these things. All right. So another thing is that, of course, we didn't talk about B. So again, for those alphas that are greater than 0, right? One of the conditions, KKT condition, says that the constraint should be met. That means that the point should be on the margin, right? That's what we said earlier, which means that B is, you can solve B, right? We can say B will be equal to right? So you can get this B. But one thing you'll notice is that that means that you can get as many B's as there are support vectors, because you can get one B for every n for which alpha 1 n star is greater than 0. Now, ideally, what will happen is that all of them will be the same. If you are able to do perfect optimization, all B's will be equal, ideally. But of course, we are doing optimization. That means that there is some convergence issue, and so you might stop early. So it might not happen that all these B's are exactly the same. So typically what they do in any SVM implementation is that they take B, one B, so that they calculate all the B's for all n's, and then you can either take a average, or you can take sort of some kind of an averaging. So in fact, in the slides, I have a formula which you can use. The B will essentially be, you take all the negative examples, right? And you compute the B using that, and take the one that gives you the max value, and then take the positive examples and take the one that gives you the min value, and take an average of that. So it's kind of a heuristic, right? Ideally, for all n's, you should get the same B because they're all satisfying the constraint, but that will not happen. So we do this sort of a averaging business. All right? Any questions so far? So essentially, we have concluded the SVM training, right? Because we have first solved a quadratic programming problem, which is over here, to get our alphas, and then we have plugged them back to get W like this, and then we have plugged them back to get B like this, right? So now we have W, we have B. A new data point comes, we can easily compute W transpose X star and C plus B, and if it's on this side, it's positive, other side's negative, right? Very easy. Now another one observation that we made was that alpha n will be non-zero only if your data points are on the margin. So this helps later, because what we will see later is that in SVM implementations, they actually never compute W. They never compute W because they can just find the prediction. So remember, what is prediction? So for a test point, right? Let's call this test point X star. What we need to compute is W transpose X star plus B, and then we check if it is greater than or less than 0, right? But this W is actually, we can substitute this for, we can say that W is summation alpha n star yn xn transpose, because this is what in terms of plus B, right? So this is our decision value, so it's called V. This will be same as this, which can be written as alpha n star yn xn transpose x star plus B. Okay. So we compute B, we keep it on the side, but we actually never compute W. We can directly just use alphas, all right? And later on, we'll see why that is useful, because then this becomes an inner product, and then it helps us use kernel functions. So that will be next class. But for now, One thing I want to just point out, it will be this. And then what happens is that means that in your training, when you do your training, right, the things that you will save is not W and B. The things that you will save is B and your alphas, all right? But because only some alphas will be useful corresponding to the support vectors, it means that you don't have to save all your alphas. You will only save, so this can be actually written, this will be n equal to 1 through n, but this can also be written as alpha, only those n's for which alpha n is greater than 0, alpha 1 star yn xn transpose x star plus b, which actually means that, and alpha n is greater than 0 for only true for support vectors, which means that you will get a very concise, compact solution. Only those alphas, you will need only those alphas that are greater than 0 corresponding to the support vectors. All right, any questions so far? Okay, so this is just SVM. All right, so we've seen all of that, of course, right? Now we want to relax it. So there are two assumptions that we have made so far. One is that we are trying to learn a line, which means our inductive bias is pretty simple. And the second is that we assume that the data is linearly separable, right? As I told you last time, if your data is not linearly separable, and if you try to solve this equation, it will never converge, right? Because if it's not linearly separable, it means that some of the constraints will not be met. Okay? But that, of course, is not a very good situation, right? We want it to work also when data is not linearly separable. So how do we sort of extend that? And then later we'll see how do we extend SVMs to also learn curves, right? So first thing let's see is, what if the data is not linearly separable? And the point is that, of course, now we cannot have those strict constraints, right? But it turns out there's a very easy fix to that. It's almost disappointing how quickly this will end. So the idea is that instead of forcing those constraints that all points should be on away from the margin, right? We introduce a slack. We allow points to be little inside the margin as well, okay? But then we try to force that that slack, we sort of regularize over that slack. So we do not want all the points to be anywhere with respect to the margin, but we allow a little bit. So mathematically how we do that is like this. So this is what we do, right? So the problem has changed a little bit. Now we are saying that it is not necessary that this line perfectly separates the two types of points, right? Which means that we allow some points to fall on the wrong side of the margin, okay? We still want most of the points to be away from the margin, but some are okay. So this will allow us to learn even when our data is not linearly separable. So this value, right, how far is a point from the margin, is called slack, okay? And we are going to represent it with a Greek symbol psi or chi, I don't know. But anyway, so let's come back here. So in separable case, this is our constraint. We want our points to be either on the margin or on the right side of the margin. But in non-separable case, we relax this constraint by introducing this slack variable psi. I'm going to call it psi, I don't know what it is. So what we say is that for every training data point, there is a slack variable psi of n. And then our constraint says that this value, right, which kind of determines where you are with respect to margin, need not be greater than 1. If it was greater than equal to 1, then what we are saying is it's either on the margin or on the other side. But we're saying it's okay if it is slightly on this side. So which means that every data point has the flexibility of being on the wrong side of the margin, and the amount by which it has to be on the wrong side is given by psi, right? And the constraint on psi is that it needs to be positive, because you can only, if it is on the right side of the margin, we don't care, right? Then there is no business of psi. You are on the right side, stay there. But if you're on the wrong side, then we want to know what psi is. So that's why we treat psi n to be greater than equal to 0. And one thing you will see is that, so this value, right, this magnitude of this vector is psi. If psi is greater than 1, which means that not only is this red point on the wrong side of the margin, but it is also on the wrong side of the decision surface, right? Now, because we do not put any constraints on psi saying it has to be less than 1, it means that this formulation will also allow for some misclassification. So it's okay if your thing is on wrong, it's misclassified. So it's not going for zero training error, it's going for non-zero training error. All right, so that's the point. So some science, but we do not want all science to be very large, because then you won't get a good classifier. So what we do is we change our optimization problem a little bit. So we want to, of course, maximize our margin, right? That's there. And we want to have these constraints that your point should be within some slack of the margin. And then we also want to minimize the sum of the margins. So what this quantity does over here is that it ensures that not too many points are away on the wrong side of the margin, right? But it does not put any hard constraints saying which one should be on the right side. All it says is that let's define this new sub-objective function added to our optimization formulation. So if you solve this, right, what will happen is that it will try to maximize the margin, but also allow for a little bit of slack, all right? And C is a constant that you provide. What C does is that it controls how much you want to maximize the margin and how much you want to allow for a little bit of slack, right? So geometrically, we can look at that. Any questions so far? It's all very mesmerizing, yeah? So let's say our data looks like this. So we have some positive points, we're going to denote them by triangles, and some these points, right? Circles. Now it looks like we can't draw a line, right? So, can't see that. Sorry. Let's say these are two types of points I have, right? So we cannot draw a line. So what now this new formulation will do is that it will draw a line, right? And then of course there will be some margin. And then some points will be on the wrong side of the margin, right? So the idea is that it can either draw this as the line and this as the margin, right? Or it can draw maybe slightly different line and a little bit of a smaller margin, right? So both are solutions that are acceptable now, because anyway all bets are off in terms of linear separability. But which one to choose, right? So what you will see is that in this case, the blue one, right, maybe the margin is small, W is small, sorry, the 2 over W square will be small for this one. But the slack penalty is also small, right? Because very few points are on the wrong side of the margin and they're wrong by a little bit. Whereas for the red one, 2 over W square is larger, right? So, but summation is right. And here this is larger, is also large, right? Because you're accommodating more slack. So what that C lets us do is control between that. Should we choose this or should we choose this, right? You want to keep your margin as big as possible, but you do not want to accommodate too much slack. So that trade-off is balanced by that C. So when you use support vector machines, which you are going to use for your programming assignment, you will be asked to play around with this C. So C is a parameter, right? One thing about the assignment is that we do not actually want you to implement support vector machines, because support vector machines, because of this issue that you need to do a quadratic programming thing here, right? So it becomes a little more cumbersome to implement it. So I don't want you to do that. But what we are going to do is we are going to use a package in sklearn and play around with the parameters. So what happens if you increase C, reduce C, what happens to your accuracies, right? So another thing that you can also see is that so what is the role of C, right? So basically what C is doing here is it's trying to balance between how much error are you willing to concede versus how much margin you want to have, right? So it has actually a same effect as the regularization parameter. So regularization parameter lambda also balances between your training error and your complexity, right? We have seen that the margin actually is the inverse of the complexity, right? Because you're trying to minimize W transpose W, which means maximizing the margin. So it has the same effect. So the slack, the sum of the slack values, this could be treated as your training error. This is how much you accommodate the error. And the other part, this part can be treated as the complexity. So C has the same effect, very same effect of balancing between the two. All right. One thing that becomes different. Okay, now how do you solve it? Sorry, I forgot to mention that. It turns out that you can use the same formulation, the dual formulation here as well, because nothing much has changed. You just have introduced some new variables. Yeah. Yeah, this is going to minimize. I'm sorry, this is going to minimize. It's the same optimization problem. This is a mistake, but you're trying to minimize this, which is maximize the margin plus the total error. So everything is still the same. You can do the same QP formulation. You'll get the same expression for W as a function of your alphas. And then, but the only thing that will change now is that your support vectors will not just be the points that are on the margin, but it will also include the points that are on the wrong side of the margin. Okay, so the ones that are inside the margin, because alpha will not be 0 even for those points. So it will be 0 only for points that are on the right side of the margin, but support vector, the number of support vectors that you'll have will be higher. All right, what is the time? 3 minutes. All right, so this is support vector machines in its very plain vanilla form, and then we are going to talk about how to extend it for non-linear situations. But there's one discussion I want to have quickly before they throw us out. So I'm going to start it, and later on we'll sort of conclude, right? So what we have done so far throughout the course, we have looked at 3 linear classifiers, right? Logistic regression, perceptron, and support vector machines. And I have talked about this many times. But all of them have very similar nature. They all have a W, right? And they all look at, is the W transpose X greater than 0, less than 0, right? But the difference is how you train, which means the difference is how you set up your optimization problem, okay? And it turns out that all of them do it in a slightly different way. So the solution that you get is a little different, okay? Now, this is a very generic classifier optimization problem, right? So let's look at this. What we are trying to do here is we are trying to learn your W and B. Now here I'm assuming even in perceptrons and logistic regression, we have kept the bias term out, right? So let's say we have a general classifier. There is W and B that we want to minimize. So what we what we should minimize is the number of examples that we make an error on, right? So this kind of tells you if this is less than 0, then that means that you made a mistake, right? Because if yn was positive, then if it was on the right side, this should be positive, and if y was negative, this should be positive again, right? So these are the number of times you make a mistake. This I function just counts it. It's called an indicator function. It just counts how many times this was true, right? So this counts the number of errors, plus there is a regularization that we'll talk about later, all right? So there's a loss function and a regularization, and we want to find an objective function. We want to find a solution which minimizes the loss but also keeps things simple according to a regularizer. But this loss, right, this is called the 0-1 loss. It's hard to optimize. Why? Because it has a very sort of discrete form, right? So let's say you had only one data point, then this loss can either be 0 or 1. You would either make a mistake or not make a mistake, right? So it's a 0-1 loss. If you have 4 data points, then it would either be 0, it could be 1, 2, or 3. So the problem becomes that we do not have good mathematical tools to solve an optimization problem in which your objective function takes discrete values, right? And that is why what all of these different classifiers do is, instead of doing this, they relax it. They make it continuous smooth, right, in different ways, and then try to solve that, right? So the point being that This problem is NP hard to solve in computational complexity terms, which means that you cannot come up with efficient algorithms to solve it. So what we do is we change it. We approximate this 0-1 loss by different loss functions. So for example, in support vector machines, we use something called a hinge loss. And next time I'll show you why it is a hinge loss. In perceptrons, of course, we use a squared loss. In logistic regression, we use a log loss. All right? And all of them sort of approximate this 0-1 loss in different ways. And that is why we get different answers. So next class, we'll discuss about that a little more. Any questions so far? All right, so I'll see you on Friday. Thank you very much.